Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to a new topic. The topic is about statistical estimation techniques. As we have seen, data mining, data assimilation, and prediction are three pillars of data science. Deterministic model, deterministic methods of estimation of parameters in least squares setup. But more often than not, observations are not deterministic. They are affected by noise. So we need to be able to have a probabilistic model for the noise affecting the observation. So we need to have a probabilistic statistical characterization of the estimation process, and that's what we are going to overview in this class of modules. So, statistical estimation problem. Let X be an unknown. Let X be an unknown vector to be estimated. X can be thought of as a true state or the true state of the system being observed. Mother Nature is very tricky. She doesn't reveal her true state, but she indicates her state through observations. So X is not directly observable, but it is a function of X. But the observations are not directly related to the state itself, but a function of the state. So Z is called the observation, X is called the state, and the mapping that goes from X to Z, H, that's called the measurement system. When H is a linear, Z is equal to H of X, is a linear measurement system, otherwise it's nonlinear. So this we have called the state space. This is what's called the observation space. And H is a mapping from state space to observation space. State space is Rn, observation space is Rm. Generally, Z, the observations, are affected by noise, and V is supposed to be capturing the measurement noise. So we are going to make a first fundamental assumption. X is the true state of Mother Nature. V is a kind of observational errors associated with the observation, with the measurements. It is assumed that the observing system does not affect the Mother Nature too much. It is assumed that the Mother Nature, state of the Mother Nature, the observational errors are uncorrelated. There are special cases where the observational errors could be a function of the state. That could be a more complex formulation. So we are going to model the observation as a nonlinear function of the state plus an observation noise. You may remember that the earliest work relating to modeling the observational errors is due to Gauss. So in trying to invent the least squares theory, he was interested in analyzing the errors in the observation, and he at that time discovered that observation errors are distributed according to Gaussian distribution. He didn't call it Gaussian, we call it Gaussian in honor of his discovery. We are assuming that This noise is such that it is normally distributed or Gaussian distributed. Its mean is 0 and a covariance is R. Let's look at this now. This Z is a m by 1 vector. This h of x is a m by 1 vector. So the observation is also an m by 1 vector. This vector is such that its mean is 0 and its covariance V is R. There are two things I want you to understand. It should be V transpose. I apologize. That's the matrix. Please understand, V transpose V is a scalar, is the inner product. V transpose is an outer product matrix. So it should be V transpose that is equal to R. I am assuming R is a function of the instruments. R is a m by m matrix. In general, R, we are going to assume it is symmetric and positively definite. A special case where R is a diagonal matrix. Please understand, R is a matrix whose diagonal elements are going to be variance components. I am assuming you are all familiar with basic probability theory. The diagonal elements of the covariance matrix are variances. The off-diagonal elements are cross covariance, covariance between measurements at station I and station j, or element zi and zj. So what is it sometime could happen? The vector z is such that the measurement noise affecting the components zi and zj are not correlated. In that case, this is 0, this is 0. So in general, R could be an SPD matrix. In special case, it could be a diagonal matrix. In further special case, R could be sigma square I, where all the diagonal elements are essentially the same. Under what condition all the diagonal elements can be same? If I am using the same instrument to measure all the different parts of Z, then I can assume that the variance affecting all the observations are the same. The noise affecting different components of the observation are uncorrelated. So there is a whole family of assumptions. Z could be SPD, D could be diagonal, D could be a diagonal with a constant diagonal elements. Now, there are two approaches. There are two ways to model the unknown state. One is due to the Fisher school, Reynolds-Fisher. Another is the Bayesian school. In the Fisher school, it's assumed that x is a constant mu. The unknown parameter to be estimated is a constant. Fisher introduced the notion of what's called the maximum likelihood method to be able to estimate this unknown constant, and it relates to what's called the point estimation. Because if x is a constant vector, mu is a vector belonging to Rn. It is a point in the n-dimensional space, so it's called the point estimation. So in Fisher school, the parameter assumed to be a constant but unknown. It relates to point estimation, and he developed the method of maximum likelihood, which you are going to introduce very quickly. So this is the Fisher school of thought. Another is the Bayesian method. In the Bayesian method, x is considered to be random. When I have an unknown random quantity, the observation z is going to reveal information about the unknown x. For example, your blood pressure reveals a position of your heart. The functioning of your heart. The blood test tells you about the cholesterol in your bloodstream, and so on. So observation reveals truth about Mother Nature. So when x is random, oftentimes I may have some prior information about the random variable. For example, is there a life on the moon? Before moon landing, we did not know anything about it. Now we know that there is no life as we now know in the earth, and they are trying to find out whether all other forms of life in moon or Mars and so on. So there is a random variable x. The observation reveals information about the random variable. The random variable is such that its expected value is mu. Mu is the mean of the unknown random variable x. And I am going to have two pieces of information. One is the prior knowledge. Before conducting the experiment, I have some feel about what the values, what is the range of values x can take. So that information is called prior information. Then the actual observation comes in. Then we combine the two to get what's called the posterior. Posterior is after, prior is before. Before the experiment, after the experiment. So after the experiment, I'm going to revise my prior to get the posterior. And so if there is no observation, I simply go with my belief. If the observation comes in, the observation reveals information about the mother nature. I'm going to combine the prior with the observational information. The process of combining them is called the Bayes rule, and the combined information is called the posterior distribution. So in this case, we are going to be working in the space of probability distribution, prior distribution, conditional distribution, information about z given a given value of the unknown is called conditional distribution, which reveals information that the observation has about the unknown. Then combining the two is called the posterior. And I want my posterior distribution of x to be such that its expected value must be equal to the mu. What is mu? Mu is the mean of the unknown. So, given H, what is our H? H is the map that maps the state space to the observation space. Now I am going to, so look at this now. This is Rn, this is Rm, here is x, here is z, and this is H. So I want information, I want to be able to estimate x, but I am working in the space. So I have observations. So I have to process the observation to be able to get the information about the unknown. So what is that I am going to do? I am defining a function from observation space to the model space, phi, Rm to Rn. So if you give me z, phi of z is x hat, and x hat is an estimator of x. X hat is an estimate of x. This function phi is called the estimator function. So estimator function takes the observation and puts out an output x bar, and x bar, x hat. X hat is the estimate of the unknown x. For example, what is the idea here? If I am looking at the cloud system using a radar sends signals into the cloud. The water droplets in the cloud reflect the radar energy. The radar receives the reflected energy. The reflected energy is an indication of the amount of water contained in the cloud system. It is based on this reflectivity we are able to predict that there will be 5 centimeters of rain or 10 centimeters of rain or 2 millimeters of rain. So it is the reflected energy received by the radar has information about the reflecting medium, which is the cloud system, and the amount of rain contained in the cloud system. Now z is random and phi is a function. Therefore, the output of phi, the output of the estimator function is a random variable. So everything is random now. Now what is that we want? We want to be able to obtain the probabilistic characterization of the estimate. This requires some discussion. What is the best information I can have about a random variable? The best information I can have about a random variable is the probability distribution. are the probabilistic characterization of the random variable. For example, if I am tossing a coin, the output is random, head or tail. We say the output, the head can come with probability P, the tail can come with the probability Q, P plus Q is 1. So that's the best thing we can do. If P is half, Q is half, we say it's a fair coin. So the best way to describe a random variable, a complete way of describing a random variable, is to characterize the probabilistic distribution, the probability distribution of the random variable. If phi is a linear function of z, it's called a linear estimate, otherwise it's called a nonlinear estimate. So in my formulation, both linear and nonlinear estimation are embedded within this framework. As we said earlier, there are two approaches. The Fisher's approach. Fisher's approach, z is equal to h of x plus v, and v is assumed to be a zero mean covariance or Gaussian noise. N refers to a normal distribution, Gaussian distribution, they are the same. So what is the assumption here? X is unknown. X as a parameter value is a fixed constant. Mother Nature has fixed that constant, X, and she doesn't tell us. But I can get information about H through Z. Z is equal to h of x plus v. So h of x contains information about v, about x. But v is not equal to h of x. V equal to h of x in the deterministic analysis. In the statistical analysis, z is equal to h of x plus v. So the noise correcting the observation. Since the Mother Nature has already picked x but did not tell us, now we can say what is the distribution of the observation given x. Given x. So, since h is a deterministic function of h, this can be computed. I know the distribution of v, therefore I can compute the distribution of z, and that is called the conditional distribution. The conditional distribution of an observation given an unknown x. X is unknown, but pz, the conditional distribution, is known. So, if I took this information, combining it with, and v is this, therefore, if I compute the mean of z is equal to h of x, if I compute the covariance of z, that's also equal to r. That's also equal to r. So what does this mean? If you add a constant to a random variable, its variance doesn't change, only the mean changes. The mean of v is 0, h of x is a deterministic quantity, so the mean of z is h of x. The covariance of z is the same as the covariance of v, therefore z is distributed according to the normal distribution with mean h of x and covariance equal to r. So this comes from basic probabilistic analysis. There are two ways, given z, I would like to be able to estimate x. There are two ways of doing it. One is called the maximal likelihood method, another is called statistical least squares. Statistical least squares. We are going to talk about these two. Deterministic least squares, that's what we indulged in the previous modules. Now we are going to be talking about statistical least squares, which runs parallel to the deterministic theory. So, what is the idea here? In Fisher's framework, I am given an observation. You have a map that maps the model space to the observation space. I know how to model the observation noise. So if I know the distribution of the model, the distribution of the observation noise, using this is the model, I can characterize the probability distribution of z, which is given by this. So z has a distribution whose mean is h of x and x is unknown, or is a covariance matrix that is known, I would like to be able to, so given z, I would like to be able to estimate x. That's the estimation problem here. There are two ways. One is called the maximal likelihood, and another is called the least squares. On the other hand, in the Bayesian approach, what is the idea here? I'm assuming prior is given or known to me. We have opinion about anything in life, right? Who will win the election? Election results are going to be random. Some people make predictions. We all know. So our prior information about the election is biased by our own desires and analysis of the situation. So I have prior situations to predict this party will win. Then the election happens. The results comes in. Either your prediction comes true or your prediction is not true. So prior is the previous belief. The conditional distribution Pz of x, please understand the Pz of x conditional distribution, they are essentially the same in here. Now I'm going to relate the conditional distribution to the joint distribution. This is called the joint distribution of x and z. We all should know from basic probability theory, the joint distribution is the product of the conditional distribution and the prior. And I can condition it either on x or on z. So this is the standard rule that comes from basic probability theory. The joint distribution can be expressed as the product of conditional distribution and a prior. So these two are equal. These two are equal. If these two are equal, I'm now going to consider Px of z is equal to Pz of x times P of x divided by Pz. So this is called the posterior. This is called the posterior. This is the prior. This is the conditional distribution. This is the density, this is the probability distribution of the observation. So from basic definitions, I can rewrite the numerator to be this. The denominator P of z is simply the marginal distribution obtained by integrating the joint distribution with respect to the state x. With respect to the state x. And this expression is equal to Px of z. So I originally started with some ideas about Pz. The observation reveals information about x. I combine the two, I get new information about x based on z. New information about x based on z. So the observation affects my prior. This transformation is called the Bayesian approach, and this formula is called the Bayes rule. Bayes rule. When the posterior is calculated, then we can use this in a variety of ways. I can compute its mean, I can compute its median, I can compute its variance, and so on. So this is the combined information that comes from here, posterior. So these are the two major competing frameworks for statistical estimation. These are not the only two, but there are others, but these are primarily the basic methodology. So Bayesian approach needs extra information about the prior. Maximal likelihood or least squares do not require prior. Both require conditional distribution, and this is the general setup for statistical estimation, at least to get started. So now we talked about an estimator, an estimate. Estimate gives the value of the unknown. So I have the state x, I have an estimator x hat. So please remember, I am going from x to z. This is Rn, this is Rm, this is h, this is phi. The phi of z is equal to h of x, phi of z is equal to x star, and this is the estimate. So I have x star coming here, x is the unknown. So I would like to be able to understand the relation between the unknown x and its estimate x hat. Please understand, the unknown x is a constant in Fisher's approach. The unknown x is a random variable in Bayesian approach. In either approach, I am going to get an estimate. The estimate x hat can be obtained by maximal likelihood or least squares method within the Fisher's framework. It can be obtained, the information about x hat can be obtained as a probability distribution, the posterior probability distribution in the case of Bayes' rule. So now I am going to describe the properties of good estimates. When do I say an estimate is a good estimate? What are the properties? The properties are: an estimate must be unbiased. An estimate must be relatively efficient. I need to express the notion of the efficient estimate. An estimate must be consistent. And there are what's called sufficiency conditions for an estimate to be a good estimate. So unbiasedness, efficiency, relative efficiency, consistency, and sufficiency of estimate. Sufficiency of the function phi. What does sufficiency say? This function, which is the function of z mapping to the state, has enough richness to be able to get a good estimate. So consistency, efficiency, unbiasedness, these are technical concepts. We are going to introduce each of these concepts as we go by. So first, unbiasedness. Unbiasedness relates to the relative location of the mean of the sampling distribution. So now I will talk to you about something about the sampling distribution. Suppose there is a coin that falls head with a probability p and you don't know what it is. I'm going to conduct experiments. Let's assume I'm going to toss the coin n is equal to 100 times. So let us define a random variable xi. Xi is equal to 1 if head, is 0 if tail. Therefore, if I toss the coin 100 times, I'm going to get p hat, the estimate, is equal to 1 over n times summation of xi. I is equal to 1 to 100. So this is called sample estimate. So what is so this is the function phi of x1, x2, x100. x1, x2, x100 are the samples. In this case, I may even say this is equal to n, this is equal to n. So there are n samples. The function of the n samples is the average of the n samples. The average gives you the estimate. So this is the estimator, and this is the estimate. Let's suppose I repeat this experiment. Please understand, the p hat must be in between 0 and 1. P hat must be in between 0 and 1. So let's assume I'm going to repeat this experiment 1,000 times. L is equal to 1,000 times. I'm going to repeat this experiment 1,000 times. So I will have 1,000 different estimates of the probability it falls head. If you plot these 1,000 values, they will all cluster around in small neighborhood here. So this is the interval over which all the 1,000 values are going to cluster around. So if I have these 1,000 values in here, I can talk about a histogram. I hope you all understand how the histogram is all about. So I can try to talk about the histogram of these. This histogram then can be approximated by a continuous distribution. This distribution arising out of histogram is called sampling distribution. Sampling distribution. This sampling distribution contains information about the unknown. It's a probabilistic characterization of p hat. So first, this notion of sampling distribution. So what is a sampling distribution? You repeat the experiment a large number of times get the values of the estimate and draw a histogram and smooth the histogram, this histogram is given describes the probability of the estimate x hat given x. X is the unknown. Here in this particular case, x is equal to p. The unknown is p. So given x is equal to p, I am going to get x hat is equal to p hat. And for each 100 tosses, I get a value. If you do 1,000 times, each time 100 tosses, it is easy to visualize that all the values are not going to be the same. They are going to be distributed in a small interval. I can draw a histogram. I can have a sampling distribution. That's what the sampling distribution is all about. So many of the properties of the estimate can be gleaned through the sampling distribution. So what is unbiasedness? This sampling distribution is a probability distribution. If there is a probability distribution, it has a mean, it has a variance. The mean of the sampling distribution relates to the location, and the variance of that it relates to the spread. So it relates to, so unbiasedness relates to the relative location of the mean of the sampling distribution. I hope you got the idea now. So it stands to reason to expect that the unknown p must be the mean of the sampling distribution. That means all the variations in p hat are going to be distributed around the actual unknown p. P could be half, p could be 3/4, whatever the p is. So it stands to reason to expect that the expected value of the random variable x hat given x is equal to x. So if the mean of the sampling distribution is equal to the unknown we are looking for, the unknown x we are looking for, then we say it is unbiased. And this is the case when x is a constant. When x is not a constant, this x is a random variable. So conditioned on this random variable taking the value x, I have the sampling distribution whose expectation is given by the inner expectation. So the inner expectation is based purely on the results of the random experiment, conditioned on a specific value of x. But since x is random, x itself is a random variable, so I can take another expectation with respect to x. So the inner expectation is with respect to the results of the random experiment of tossing in this particular case. The outer expectation is the choice of the value x that Mother Nature picks from the prior distribution. So this is called nested expectations or repeated expectations or iterated expectations. Based on the probability theory, the repeated nested expectation is equal to expected value of x hat. If the expected value of x hat is equal to E of x, now please understand, x itself is random. Therefore, what does this second equation say? If the expected value of the sampling distribution coincides with the expected value of the unknown x, the distribution of the unknown x when x is random, if these two are equal, we call it unbiased. So these are the two ways in which unbiasedness can be described. So please understand, this is with respect to the prior. That's what we already talked about. So I'm considering both the cases, x being a constant and x being a random. So the difference between E of x bar and x in the first equation, the difference between E of x bar and E of x from the second equation is called the bias. If this bias is 0, it's called unbiased. Now it stands to reason. That's why we are able to estimate the probability that a coin falls head. The probability p we are able to estimate using these kinds of simple experiments. these kinds of simple experiments. So bias, unbiased, when X is constant, when X is random. When X is constant, when X is random. So I'm going to illustrate this by an example. Let's consider the coin tossing experiment. It falls head with the probability P, it falls tail with the probability Q, 1 minus P. The unknown is X. X is a constant, P. Given the results of m independent tosses of a coin, please understand, this coin tossing is a Bernoulli random variable. X is equal to 1 if head, X is equal to 0 if tail. This is called the Bernoulli distribution. 0, 1, this is P, this is Q. P plus Q is what? P plus Q is equal to 1. So I'm trying to make m tosses, and we all know the results of the previous toss does not affect the future task. So tosses, so it's called independent. So given the Bernoulli distribution, you should be able to verify that the expected value of z, so this is the observation, let's say x, this is the observation, sorry, this is the observation z is equal to 1 of that. So the expectation of z is equal to 1 times p plus 0 times q, which is equal to p. The variance of z, you all know the variance of z is equal to z minus expected value p. So z takes the value, z takes the value 1 minus p square with the probability p plus 1 minus 0 square with the probability q with the probability, I'm sorry, it is 0 minus p, sorry. It takes the value 1, p is the mean value. It takes the value 0, p is the mean value. The difference between the actual value and the mean, is what we have. So 1 minus p square times p plus minus p square times q. So this is q square p plus p square q. This is equal to pq times q plus p. Q plus p is 1, that is pq. So the variance is pq in a single trial. So z is equal to 1, z is equal to 0 with the probability p, with the probability q. That's exactly what I'm defining here. This is a Bernoulli distribution. Bernoulli distribution. So in our notation, so this is what you would have done in your calculus, in your basic probability theory course. I'm now going to translate it into our notation. X is the unknown, z is here, zi. So I'm trying to say z is equal to h of x plus v, h of x, z is equal to h of x plus v. H of x in this particular case, z is equal to p plus v. So zi is the ith toss, vi is the noise affecting the ith toss. Vi is equal to 1 minus p with the probability p, vi is equal to minus p with the probability q. Why is that? We already know that. If zi is equal to 1 is equal to p plus vi, so that happens with the probability, p. So if vi is equal to 1 minus p, this is 1, that happens with the probability p. And zi is equal to 0 implies p plus vi, and vi is equal to minus p, so p plus minus p, that's equal to 0, that happens with the probability q. So vi is equal to 1 minus p with the probability p, and vi is equal to minus p with the probability q. is the same as z is equal to 1 and z is equal to 0 with the probability p and q respectively. Therefore, I can rewrite in my notation, this is the estimate, this is the properties of noise. The noise property is such that its expectation is 0, please verify that. Noise properties are such that its variance is PQ. Expected value of Zi is P, the variance of Zi is PQ. So this result is the same as the previous result, but I am rewriting it in a new notation. It is in this notation of 8 we do in probability theory. It is in this notation of slide 9 we do in our discourse. They are essentially the same except for the notation. So an estimator is the sample mean. A good estimate is a sample mean. What is the sample mean? P hat is equal to 1 over m time of the sum. Zi is equal to 1 to m. So expected value of P hat, I'm using a probability rule. Expected value of the sum is the sum of the expectations. So E of summation of xi is equal to summation of E of xi. That's the rule I'm using. Expected value of the sum is the sum of the expectations. The sum of the expectations. So each of these is equal to P. I'm adding m times mp divided by m, that is equal to P. Therefore, this P hat is such that its mean is P, its sampling distribution, the mean of the sampling distribution is P. Therefore, this estimate is an unbiased estimate. Now I am going to compute the variance of P hat. The variance of P hat is Zi minus P, because that is the probability definition of the variance. So variance is the expected value of 1 over m times I is equal to 1 to m Zi minus P whole square. I have already explained this in computing the variance at the bottom of the slide 8. By applying the same rule, I am writing this is the variance formula. So 1 over m square comes in here. This is the variance of the single toss, and this is equal to PQ. This PQ is independent of I, so they are going to add this m times. So MPQ divided by m square is equal to PQ by m. Look at that. The mean remains constant, but the variance is inversely proportional to the number of samples. Therefore, the distribution of P hat, the sampling distribution of P hat, you remember the sampling distribution we talked about, has a mean equal to P, and the variance tends to 0 as m tends to infinity. That means as you take more and more number of samples, the variance tends to 0. So what does this mean? The sampling distribution tends to a delta distribution located at P. This is the delta distribution located at the point B. So P hat is an unbiased estimate of P. P hat is an unbiased estimate of P. So in the coin tossing experiment, I have an unknown probability of coin falling head, and I am able to establish a simple experiment by which I can estimate this unknown. And this estimate is such that it is unbiased. And asymptotically, as the number of samples goes to infinity, its variance becomes smaller and smaller and smaller and smaller. I'm sure you should know that in the case of a Gaussian distribution, the unit Gaussian like this, if the variance becomes less and less, it becomes more and more peaked. So variance is a measure of the spread. If the variance becomes smaller and smaller and smaller, it becomes more and more deterministic quantity. In the end, when variance becomes 0, it becomes a single number. That number is P, and P is the mean of the sampling distribution. So this is an asymptotic result. It is this asymptotic result that gives us the basis for many of the statistical conclusions that we are going to make. We want to find out why are we interested in having estimates which are unbiased. In order to understand the role of unbiasedness in estimation, I am going to consider what's called the mean square error in x hat. Please understand, this is the true unknown. Here is x hat. X hat is a random variable, x is a deterministic variable. So x hat is going to be distributed in and around x, for example. If x is the unknown, x hat can be anywhere in this interval. X is an unknown, x hat can be anywhere in this interval. The mean of x hat is equal to x. The variance of x hat shrinks as the m goes to infinity. That's the idea that we have seen. So while we have seen that, I want to be able to argue why are we interested in unbiasedness? What is the impact of an estimate being not biased? I'm sorry, not unbiased. That means, what is the impact of an estimate being biased? To consider that, or to analyze the impact of unbiasedness, I'm going to consider the mean square error. What is the mean square error? X hat minus x is the error in the estimate. X hat is the estimate, x is the unknown, but the true value, the difference is called the error. Please remember, we have talked about the errors, several residuals, errors, these are all related quantities. X is not random, but x hat is random. I'm computing the square of that. I'm taking the expected value. Taking the expected value is called mean. So it is a mean square error. It is equivalent to the sum of squared errors that we saw in least squares theory. Sum of squared errors, expected value of the square of the error, mean square error. So this is called the mean square error, MSE, mean square error. I can add and subtract a quantity called E of x hat. What is E of x hat? The expected value of the random variable x hat. I can add and subtract, nothing changes. So now this is one quantity, this is another quantity. I consider this as A, I consider this B. So this is like expected value of A plus B whole square. So expected value of A square, expected value of B square, expected value of A times B, 2AB. Now I'm going to look at the term. X is a constant. X hat is a random variable. E of x hat is the mean of the random variable. The mean of a random variable is a constant. Therefore, the difference between E of x hat and x is a constant. So consider this cross term. In this cross term, here is x hat minus E of x hat. X hat is random, it's mean, so this is a random variable. We just saw E of x hat minus x, that's a constant. We all know expected value of A times x is equal to A times expected value of x. Multiplying a random variable by a constant, I can bring that constant outside the expectation operator, that's a standard rule. So I can bring that constant out. So this term, the cross term 2 times that, now becomes equal to this. Now becomes this. So what is that I have? This is, so it becomes expected value of x hat minus, so what is the cross term now becoming? The cross term now becomes 2 times the expected value of x hat minus x times expected value of x hat minus E of x. So this is the constant out. Now expected value of the sum is the sum of the expected values. Expected or the difference of the expected value. So this is equal to 2 times E of x hat minus x times E of x hat. This is already a constant. Expected value of the constant is itself. So this is E of x hat. Please understand, this is E of x hat minus E of x hat. This is that. But these two are equal, therefore this is 0. I am going to multiply it by 0. So the second term becomes 0. That's what the argument here is that. Now, if the second term is 0, now look at the difference. Look at the definition of a bias. E of x hat minus E of x is called the bias. E of x hat minus x is called the bias. So from the definition of the bias, now we know I have this quantity. So the third term is vanishing. The first term is there. The second term is there. So the mean square error x hat, now this equation now becomes the first, this is the first term that is coming in here. I'm sorry, that's not right. This is the term that is coming in here, that's right. Now let's look at this now. This is x hat, this is E of x hat, the square, expected value of x hat minus E of x square, what is that? That by definition is the variance of x hat. This by definition is the bias that we have already talked. This by definition is the bias. Expected value of x hat minus x is the bias. So that's bias square. Look, go back to the definition of the bias. Either this or that is the bias. So you can really see this quantity is the square, it's the square of the bias. So this is the bias square. So the mean square error is equal to the variance of x hat plus the bias square. Now when will the mean square error be minimum? I can't change the variance of x square. The variance of x square depends on YAM, nothing else. The number of samples we have already seen. Bias square is a positive quantity. So the bias adds to the mean square error. So if I want to minimize the mean square error, the bias has to be 0. The bias has to be 0. The bias has to be 0. Therefore, the variance is minimum, the mean square error is minimum if the estimate is unbiased. So minimizing the mean square error is equivalent to minimizing the total variance of the estimate. That's why we always require the bias to be 0. So we talked about what are the various things we have seen? An unknown could be a constant or a random variable. We talked about 2 competing frameworks. We are interested in the properties of estimator. The estimate must be unbiased. We define what biasness in both the cases when x is random and not random. We showed the requirement of unbiasedness is related to minimizing the mean square error. So the mean square error is equal to the variance if and only if the bias is 0. And that's the reason why we are interested in making estimates which are unbiased. Now we are going to relative efficiency. Let x hat A and x hat B be 2 estimates of the unknown. We say estimate A is more efficient than estimate B if the variance of the estimate A is the variance of less than the variance of estimate B. So the variance of the estimate relates to the spread of the probability distribution. If the variance is less, means the sampling distribution is much more concentrated. The more the sampling distributions are concentrated around its mean, more efficient the estimates are going to be. The ratio of xb to xa is called the relative efficiency. Xb to xa is called the relative efficiency. So we say one is more efficient than other if one estimate has a lesser efficiency, a lesser variance than the other. So the relative efficiency relates to the ratio of the larger to the smaller. You can also define it to be xa to xb if you want to, but you know the understanding of 2 efficiencies. I am trying to talk about the ratios between them. Now let's look at this, the coin tossing experiment. In the coin tossing experiment, we have already seen if m is equal to 1, if m is greater than 1, in this particular case, the estimate is P, the variance is PQ. In this particular case, the estimate is P, this is PQ by m. So, PQ by m for m is greater than 1 is always less than PQ. Therefore, if I have more samples in the coin tossing experiment, the estimate arising out of m tosses where m is large is more efficient than estimating the probability that a coin falls head with just one experiment. So, PQ by m is less than PQ for any m greater than 1. So, what is that we are saying? XA is equal to P hat coming from m experiments, XB coming from one experiment which is ZI. So, the variance of ZI is PQ, variance of P hat coming out of m experiments is PQ by m. PQ by m is definitely less than PQ. Therefore, the mean is more efficient than a single realization. This is the reason why we are going to toss a coin more number of times. So, the more the number of samples you have, better it is. Relative efficiency. The question of relative efficiency now brings us to another important question. Is there a most efficient estimate? Once you know something is better, we would like to be able to get to the bottom of that. So, the answer is yes, and this is obtained by what is called the maximum likelihood estimate, which you will see in the future module. The maximum likelihood estimate is the most efficient estimate, and that was a result proved by Fisher. He proved these results in the early part of the 20th century. He is one of the founding fathers of modern statistical analysis. So, in his honor, the maximum likelihood method, which leads to the most efficient estimate, is one of the fundamental and the lasting, enduring contributions of Fisher to statistics. The second question is this: could it happen that a biased estimate may be more efficient than an unbiased estimate? That's also yes. Please understand, there is a whole area, books written on statistical estimation theory. I am giving you a quick sample of results from this deep theory of statistical estimation. These are topics that are covered in the statistical literature. I want to whet your taste. Hope you will be able to perform this extended analysis for your future understanding of various estimation techniques. The next one is called consistency. Please remember, this is the space, x is the unknown, x hat lies in a small neighborhood around x. So, I want to ask myself the following question: what is the probability? So, another way of looking at it, this is x hat, this is x hat lies in this interval. If x hat lies in this interval, I want to ask the following question: x hat minus x, the absolute value, is greater than epsilon. What is the probability of this event happening? So, what is the probability that the estimate x hat will exceed the true value by the absolute value difference will exceed a small number epsilon? If that probability goes to 0, means what? As the number of samples keeps increasing, the distribution of x hat getting more and more concentrated around the mean, and if this probability goes to 0, we say such an estimate is consistent. Such an estimate is consistent. We have already shown in the case of a coin tossing, the variance of p hat coming out of m tosses is pq by m. As m goes to infinity, that pq over m goes to 0. As pq over m goes to 0, the spread becomes smaller and smaller and smaller. As the spread becomes smaller and smaller and smaller, the probability that the estimate will be far away from x, the true value, by a small amount, epsilon goes to 0. That means ultimately x hat tends towards x. The distribution of x hat is going to be concentrated around the unknown x. That's the notion of consistency. In probability theory, this convergence is called convergence in probability. I have not covered probability theory, the mathematical prerequisite, in my lectures. I am assuming that you have had some good exposure of basic probability theory and basic statistics. So consistency of estimate, relative efficiency of estimate. What is the most efficient estimate? Why unbiasedness? So we have been thinking of all these ideas. The next one is called sufficiency. Conditions under which the chosen random sample has enough information to obtain the required estimate. For example, you can sample anything, but the sample must be relevant to estimating the unknown. How do you ensure that the sample that you have collected is appropriate and has enough sufficient information to be able to give good estimate about the unknown? So that are conditions under which the chosen random sample has enough information to obtain the required estimate. That's called sufficiency. It is a more, this concept is more technical. Sufficiency has been dealt very beautifully in a book by Dr. C.R. Rao. The book title is Linear Statistical Inference and Replications. You may know C.R. Rao was a direct student of Sir Ronald Fisher. So Rao has done lots of fundamental work in basic statistics. He was at the Indian Statistical Institute in Calcutta. After retirement, he went to the United States. After 65, he got a professor position at the University of Pittsburgh, where he worked almost until the day he died, and it is said that he lived up to close to 100. So he has been working in this area for a good part of 20 years, 80 years of his life. And he has made wonderful contributions to, very fundamental and basic contributions to statistics. On one of his books, Linear Statistical Inference and Application, 1973, to me is a very standard reference for those of us who want to be able to work in data science. I have a copy of it. I think there is a cheap Indian edition available. If you are going to be a series about data science, I believe every one of you should get a copy of it. And it's a very good book. It's a thoroughly written book, quite mathematical. So that's a reference the sufficiency is talked about. So these are examples taken from my book, LLD 2006, Lewis Lakshmivarahan and Dal, Dynamic Data Simulation. Now I'm going to illustrate by another example. Let mu be unknown. I'm going to observe the noisy values of the unknown. Mu zi is equal to mu plus vi. I'm going to assume this is normal with 0 mean and sigma square of the variance. IID means independent, identically distributed. So what does it mean? Each of the vi comes from the same distribution, and v1 is independent of v2, is independent of v3. What does the notion of independent means? The result of the ith task does not affect the result of the I plus 1th task, or is not dependent on the I minus 1th task. That's called independent. It's called statistical independence. You remember, we have already talked about linear independence in linear algebra. So that is called linear independence. This is called statistical independence. Identically distributed means what? That the samples are coming from the same distribution. So what does a sample mean? Z bar is equal to summation, the average of zi, and the average of v is 0. So this is equal to 1 over m summation mu plus vi. This is equal to 1 over m summation mu plus 1 over m summation vi. So if I am going to take expected value of both sides, which is z bar, expected value of this, so this is equal to mu plus 1 over m vi. So the expected value of this, the expected value of z bar is equal to expected value of this, expected value of 1 over m times 1 over m times summation mu plus 1 over m times summation vi. So this is equal to mu plus 1 over m times summation expected value of vi. Expected value of a is 0, so this is equal to mu. So that's the verification in here. The variance of z bar, we have already done that. This is given by this formula, that is sigma square by m. And this z bar is a consistent estimate because its variance goes to 0. If the variance goes to 0, the condition for consistency holds good. What is the condition for consistency? The true value, the estimate, they differ by an epsilon amount. The probability of that happening tends to 0 as the number of samples are based on which x bar is calculated, the limit m tends to infinity. If this happens, we say this x bar is consistent. So the consistency holds good. Earlier we talked about Vi being a Bernoulli noise. Here we are talking about Vi being a Gaussian noise. So that's the difference between this example and the previous example. This is the normal or a Gaussian noise. Now I am going to talk about estimating sigma square when mu is known. So what is that we have? I have a normal distribution. I have a normal distribution. It is a mean. It is a variance. Let's assume mu square is known. We want to estimate mu. That's what we did in the last example. In this example, I am going to assume mu is known, but sigma square is not known. So I am going to estimate sigma square. The estimate of sigma square is the actual outcome of the ith trial minus its expected value, difference between the square and the average of that. So the expected value of sigma square is equal to 1 over m times expected value of that. And each of these terms is equal to sigma square, m times sigma square divided by m. So that's equal to sigma square. So this is an unbiased estimate. This is an unbiased estimate. So when mu is known, this expression is an unbiased estimate of the variance. Now sigma square, when you define by this, is a random variable. The random variable has a mean, which is sigma square. That means the estimator has a mean is equal to the unknown. Now I would like to be able to look at the consistency, efficiency of those estimates. So I need to be able to compute the variance of that, because that's random. It can be shown the variance of this is equal to 2 sigmas to the power 4 by m. And I would like to ask you to be able to do this as a homework problem. It's a very good standard exercise in probability theory. Very good exercise in probability theory. So as m goes to infinity, this variance goes to 0. Therefore, this estimate becomes consistent, is already unbiased. So this is an unbiased, consistent estimate whose efficiency improves as m goes to infinity. Now I am going to talk about both are not known. So look at this now. There are 3 cases now. The normal distribution with mu sigma square. The first case is mu not known, sigma square not known. So sigma square known. Here sigma square not known, mu known. Now I am going to talk about mu not known and sigma square not known. So there are 3 cases. There are 3 cases. We have talked about mu not known, sigma square known, that's the estimating the mean. Sigma square not known, mu known, that is the middle case where I have the variance not known. Here I have a general case where mu is not known, sigma square is not known. We are going to estimate both the mean and the variance. So if mu is not known, what is that I am going to do? Z hat, the mean of the observation, is a surrogate for mu. Please understand, we have already shown in the first case when mu is not known, a good estimate of the mean is the sample average. So Z hat is a sample average. So if mu is not known, I will use Z hat in place of mu. Z hat in place of mu. So I am now going to consider the more complex case where mu is not known, sigma square is not known. I am going to replace mu by Z bar. So Z bar is used in place of mu. And I know how to compute Z bar. Z bar is equal to the average 1 over m summation Ci, that's the average. Now I am going to consider estimating the variance. Please understand, to compute the variance, I need the mean. I don't have the real mean. I only have an estimate of the mean. So if you don't have the true knowledge, I use the estimate in place of that. So this is the statistical estimate of the variance of a random variable when the mean is not known, where the mean is replaced by the sample mean. The actual mean is replaced by the sample mean. Please look at the formula here. Now, expected value of Zi square is equal to sigma square plus mu square. Why is that? Real sigma square is equal to expected value of Zi minus mu whole square. Zi minus mu whole square is equal to Z of Ei square minus 2 E of Zi mu plus mu square. But mu is constant. Therefore, E of Zi square minus 2 times E of mu, I'm sorry, I'll take mu as a constant factor outside, mu E of Zi plus mu square. But E of Zi is mu, so this becomes 2 mu square minus sign, this is mu square. Therefore, this is equal to E of Zi square minus mu square. Therefore, E of Zi square is equal to sigma square plus mu square. That's exactly what is done in here. So this comes from this simple calculation. So standard definition. So from here, the expected value of Z bar square can be verified to be the variance of Z bar plus expected value of this. So I am trying to use the same formula both for Zi square as well as Z bar square. Z bar is also a random variable. So E of Z bar square is equal to variance of Z bar square plus expected value of Z bar whole square. So both the formulas essentially come from this consideration. So using this, now you can verify expected value of this. Please understand, these are very good statistical calculations. And that's going to be equal to this, and that's going to be equal to this. Verifying from here to here, I'm going to leave it as a homework problem. It's a very simple statistical application. So what does it mean? What does it mean? Expected value of S square, which is the estimate of the unknown, is equal to sigma square by m plus mu square. Therefore, expected value of E square minus sigma square, look at this now. Hey, that's the bias. See, this is the actual value, this is the expected value. So if I am going to consider this, that's equal to minus sigma square by m. Minus sigma square by m. So what does this tell you? This estimate is a decent estimate, but it's biased, and the bias is minus sigma square by m. This bias goes to 0 as m goes to infinity. So this is the definition of the bias. Please remember that. So I have expected value of this. I am subtracting sigma square from that. So I am getting this information. So this essentially tells you this estimate is a biased estimate, and I can also compute its variance. Its variance is given by this quantity. Computing the variance again is a good homework problem for you in basic probability theory. The variance in this particular case, m minus 1 by m square, you can say the numerator is m, denominator is m square, so 1 over m. The variance goes to 0 slowly at the rate of 1 over m. So the variance of sigma square is equal to 2 to the power of sigma 2 times sigma to the power 4 by m. Where do we get that from? I get it from the previous slide. The variance of sigma. What is this? This is the case when mu is known. This is the true variance of the estimate of the unknown. So the variance of, I should say, sigma hat square is equal to 2 sigma to the power 4 m is greater than 2 times sigma to the power 4 m minus 1 times m minus 1 by m square. That's equal to the variance of s square. So what does this tell you? S square is more efficient than sigma square. Wow, that's a beautiful result. I want you to understand. I'm considering two estimates. The estimate of the variance when mu is known, in which case the variance is given by number 3, equation 3. I'm talking about variance of s square when this is the estimate of the variance when mu is not known. And we have already seen the variance of the estimate of the variance when sigma is not known is biased. So S square is a biased estimate of the variance. Sigma hat square is the unbiased estimate of the variance. We now know that the variance of the unbiased estimate when mu is known is larger than the variance of the biased estimate. So even though this is biased, its variance is less than the previous case. So S square is more efficient than x square is more efficient than the estimate of sigma, which is sigma hat square. So you remember we had asked a question in one of the, could it happen that the biased estimate may be more efficient than an unbiased estimate? I said the answer yes. Here is an illustration of that. And where does this illustration come from? This illustration comes from the case where I have a normal distribution whose mean may not be known, variance is known, whose variance may not be known, mu is known, variance is not known, mu is not known. So there are three cases. In the last case, I used the mean to represent the sample mean to represent the actual mean. Using that, we not only calculated two types of estimate, one with mu known, one with mu not known. One with mu not known replacing the mean by its estimate gave rise to a biased estimate, but its variance is less. So this is an example where you cannot simply throw away biased estimates. In some cases, biased estimates may be more efficient. With that, I come to the first introduction, end of the first introduction. There are a couple of very good books I follow. Meltzer and Cohen, Decision and Estimation Theory, McGraw-Hill. 1978 is a very beautiful, thin book, about less than 200 pages. It's a very succinct introduction to basic estimation theory. It's written largely for electrical engineers, but it describes the estimation theory very beautifully. And there is another wonderful book by Sage and Meltzer, Estimation Theory and Application to Communication and Control, again largely tuned towards electrical engineers. These two textbooks, please look at the time, 1971, 1978. So these methods have been around for a long time. These are two applied books, and that's where I learned my tools. With that, we conclude our first introduction to statistical estimation. Thank you.